welcome to my next video. Let's continue where we left off. So random variables that satisfy either of the following two conditions are exponential random variables. Okay, so one, the first condition, if the random variable x sub t that represents the total number of occurrences of the phenomenon from time 0 to any given t, is a Poisson random variable. With parameter lambda t. Okay, so if that, then the waiting time until the first occurrence is an exponential random variable with parameter theta equals 1 over lambda. Okay, so 1. If the random variable x sub t that represents the total number of occurrences of the phenomenon from time 0 to any time t is a Poisson random variable with parameter lambda t, then the waiting time until the first occurrence is an exponential random variable with parameter theta equals 1 over lambda. Okay? So this is the hypothesis. This is the if part. If this, then this. Okay, and that's the conclusion. Hypothesis, then the conclusion. Okay, so so here we're finding the total number of occurrences from 0 to some time t, right? So let's say the time t was an hour, and let's say it happened 5 times in an hour, right? So that would be 5 times every 60 minutes. What theta is it's kind of like telling you the average amount of time between occurrences, right? So if 5 were to happen in an hour, right, then you would say on average it would happen 1 every 20 minutes, right? On average it would take 20 minutes for another occurrence, right, if it happened 5 every hour. And so parameter theta equals 1 over lambda. Well, that would just be So that would be like the average until the first occurrence, right? And so then you would be like waiting 12 minutes on average for the next occurrence. Okay, so that's one. Okay, two. If capital T is a non-negative random variable that is memoryless, I'm going to put quotations around memoryless, explain what that means. It is memoryless, meaning the probability of capital T greater than little s plus little t, such that capital T is greater than little t, is equal to the probability that capital T is greater than little s. For all st non-negative, for all st greater than or equal to 0. So if that happens, then capital T is an exponential random variable. Okay? Okay, so if either of these two conditions happen, then your random variable is an exponential random variable. Okay? And so in the second thing here, second condition, we'll see that in example 5.13. Okay? So in example 5.13, we'll see how condition 2 is used to conclude that your random variable is an exponential random variable, which will then lead to the solution to the problem. Okay? So condition 2, we'll see an example of that soon. Okay? All right, so these are the two conditions to say random variable is these are two conditions that means a random variable is an exponential random variable. Okay? So maybe we want to copy this down. Okay, good. Okay, so I'm going to continue with an example. Example 5.12. So example 5.12, suppose the number of automobile incidents accidents or incidents from time 0 to t in hours along a segment of highway Z is a Poisson random variable with parameter lambda t is equal to 1 over 15 t. Furthermore, suppose there is an accident there at 10 a.m. Okay, so example 5.12. Suppose the number of automobile incidents from time 0 to t in hours along a segment of highway Z is a Poisson random variable with parameter lambda t equals 1 over 15 t. Further, suppose there is an accident there at 10 a.m. Part A to this problem, this example 5.12, is find the probability there will not be another car accident along this segment of highway. For at least 24 hours. Okay, so find the probability there will not be another car accident along this segment of highway for at least 24 hours. Okay, so I'm going to let, so here's the solution. I'm going to let capital T be the amount of time until the next accident. Okay? Along the segment of highway. Okay? Okay? So then capital T is an exponential random variable. With parameter theta equals 1 over lambda, which is equal to 15. Okay, so why is that? Because it meets condition 1 on the last board, right? So condition 1 was if the random variable x sub t that represents the total number of occurrences of the phenomenon from time 0 to any given time t is a Poisson random variable with parameter lambda t, then the waiting time until the first occurrence is an exponential random variable with parameter theta equals 1 over t. Okay, so that's what happens here. Suppose the number of automobile incidents from time 0 to t in hours along a segment of highway Z is a Poisson random variable with parameter lambda t equals 1 over 15 t. That's condition 1. On the last board. So that's condition 1 to have an exponential random variable. Okay? Okay? And so here though, right here you see that lambda is 1 over 15, right? And so since lambda is 1 over 15, the conclusion is that you have an exponential random variable with parameter. The conclusion is you have an exponential random variable with parameter theta equals 1 over lambda. And so it's 1 over 15. That 1 over 15 is in the denominator. And so you get 15. Okay, so that's the conclusion of condition 1, that you have an exponential random variable with parameter theta equals 1 over lambda. And you find here that lambda is 1 over 15, 1 over 15 is 15. Okay, so that's why that happens. Okay, and so now the probability there will be the probability of no accident for at least 24 hours is equal to, well, that's the probability that the wait time capital X is greater than 24. So it's not X, it's T. T is the wait time. And so T is greater than 24. Right? T is the amount of time until next accident. So if there's no accident for at least 24 hours, that means the wait time until next accident is greater than or equal to 24. Same either way. This is the integral from 24 to infinity of the probability density function So the probability density function, remember the PDF for the exponential random variable is 1 over theta e to the negative x over theta if x is positive and it's 0 elsewhere. Okay, so that is the PDF for an exponential random variable. PDF for an exponential random variable. Okay, so the PDF for an exponential random variable f of x is equal to 1 over theta e to negative x over theta if x is positive and 0 elsewhere. And so here, we're going to take the integral of that. And so since from 24 to infinity, it's always x is positive, that's the function, that's the integrand on the entire interval there. So it's 1 over theta, theta is 15, so it's 1 over 15 e to the negative x over 15 dx. And that's equal to e to the negative 24 over 15. And that's equal to 0.2019. And that's the answer. Okay? That's the answer to A. Okay, so probability of no accident for at least 24 hours is the probability of capital T, the wait time until the next accident is greater than or greater or equal to 24. And that's equal to the integral from 24 to infinity of the PDF, which is 1 over 15 e to negative x over 15. That's because we have an exponential random variable with parameter theta equals 15. And so here's the PDF for an exponential random variable with parameter theta. Okay, so with a parameter theta, f of x is 1 over theta e to negative x over theta, if x is positive and 0 elsewhere. And so here theta is 15, you plug in 15, 1 over 15 e to negative x over 15d. And so you integrate that from 24 to infinity, that's equal to e to the negative 24 over 15, and you calculate that in your calculator, that's equal to 0.2019. So that's A. Okay, so for part B, we're going to use the fact that t is the same again, and so we're going to use this part of the solution again, so we'll keep that there. So for part B, find the probability that there will be another incident, another accident. I use the word incident here. There will be another incident on the same day. So what does that mean? Well, if capital T is the amount of time until the next accident, right, and it's an exponential random variable parameter theta equals 15, that's the amount of time you wait until the next accident, and there's going to be another accident the same day. That means the wait time has to be at most 24, right? So capital T is less than or equal to 24. Wait time until the next accident is less than or equal to 24, and that means that's the probability that there will be another incident on the same day. Okay, and so that's equal to, and so now that's just the integral from 0 to 24 of the PDF, which is the same PDF, the theta is 15, of 1 over 15 e to negative x over 15 dx. Oh, negative x over 15, yeah. Okay, and that's equal to 1 minus e to negative 24 over 15. Okay, and that's equal to 0.6068. Okay, and so this is also the complement. The probability of this event is the complement of the event in A. And so 1 minus the other probability should be this one, and Okay, and so so then let's leave it like that because that's it. So for A, the answer is e to negative 24 over 15. Okay, and for B, it's 1 minus that. Okay. Okay, so that's that example. So that's example 5.12. Okay. Okay, and so here we see condition 1 and how we apply condition 1 to conclude that our random variable is an exponential random variable with parameter theta. Okay, so now the next example, 5.13, we'll use condition 2 to conclude we have an exponential random variable, and then we're going to use that to find a probability. Okay. So we need to know that we have an exponential random variable in order to use the PDF for an exponential random variable. Okay. We need to know which PDF to use to calculate the probability. Okay? So here's example 5.13. Suppose an electrical system is well maintained so we can assume the system will not fail for at least S plus T hours, given it has not failed for at least T hours. Okay. Suppose an electrical system is well maintained, so we can assume the system will not fail for at least S plus T hours, given it has not failed for at least T hours. Okay, so assume the system will not fail for at least S plus T hours, given it has not failed for at least T hours. And is the same as the chances it will not fail for at least S hours. Okay, suppose an electrical system is well maintained, so we can assume the system will not fail for at least S plus T hours. Sorry, so we can assume the odds the system will not fail for at least S plus T hours, given it has not failed for at least T hours. Is the same as the chances it will not fail for at least S hours. Okay, so let me read that again. Okay, so suppose an electrical system is well maintained, so we can assume the odds the system will not fail for at least S plus T hours, given it has not failed for at least T hours, is the same as the chance it will not fail for at least S hours. This relates to the probability that capital T is greater than s plus t, given that capital T is greater than little t, is equal to the probability capital T is greater than little s. And this is for all st greater than equal to 0. Okay, suppose an electrical system is well maintained, so we can assume the odds the system will not fail for at least s plus t hours, given it has not failed for at least t hours, is the same as the chances it will not fail for at least s hours. That's condition 2. Right, that's condition 2 from earlier. That's nice. So that happens. That's what all of that is saying. Also, suppose, so all of this is condition 2. That's this. Okay, so this one equation is all of that. Okay, also suppose the probability it will not fail for at least 10 hours is 0.99. Find the probability. It will not fail for at least 100 hours. Okay? So this is the solution. Let capital T be the time in hours until failure in the system. So let capital T be the time in hours until failure in the system, then the probability that capital T is greater than s plus t, given that capital T is greater than little t, okay, so the probability that capital T is greater than s plus t, given that capital T is greater than little t, is equal to the probability capital T is greater than little s, for all st greater than 0. Okay. Right, so that's what I just wrote here. Okay, so condition 2, this thing, is this. Okay, so I'm just stating it. Let capital T be the time in hours until failure in the system. Then, what I just said, that squiggly line thing is this. I just wrote that here again. So by statement 2, we can assume capital T is an exponential random variable. To find theta, we see that 0.99 is equal to the probability that capital X is greater than or equal to 10. Okay, because it says suppose the probability would not fail for at least 10 hours is 0.99. So 0.99 is the probability that the t, the wait time, t is greater than or equal to 10. And so that's equal to the integral from 10 to infinity of 1 over theta e to the negative x over theta dx. And so if you keep theta constant and you calculate this integral of x, you get this is equal to e to the negative 10 over theta. Okay? And so what that means is that 0.99 is equal to e to the negative 10 over theta. And so that implies, solving for theta, that theta is equal to, if you take the ln of both sides, you'll get ln of 0.99 is equal to ln of e to the negative 10 over theta. Ln and e are inverse functions of each other, so they cancel. So you get ln of 0.99 is equal to negative 10 over theta. Okay? And so then that means, so I'm gonna have to erase. So what we want to find here is find the probability it will not fail for at least 100 hours. Okay, find the probability it will not fail for at least 100 hours. So I have to erase the example because we need this room. So I'm just gonna keep the question a problem. This is the goal. We want to find the probability it will not fail for at least 100 hours. And so here 0.99 is equal to that. E to the negative 10 over theta, right? And so ln of 0.99 is equal to ln of e to the negative 10 over theta. Ln and e cancel. You get that's equal to negative 10 over theta. So ln of 0.99 is equal to negative 10 over theta. That means that theta is equal to negative 10 over ln of 0.99. That's just using algebra. So theta here is equal to negative 10, by all of that over there, negative 10 over ln of 0.99. And that's equal to 994.99. So theta is equal to 994.99. Okay, and so now that we found theta, so this means that the probability system will not fail. System will not fail for at least 100 hours. Okay, so this means that the probability the system will not fail for at least 100 hours is equal to the probability that capital T is going to be equal to 100. This means the probability the system will not fail for at least 100 hours is the probability T is going to be equal to 100 to equal to 100. And that equals the integral from 100 to infinity of 1 over 994.99 e to the negative x over 994.99 dx. And so you calculate that integral, and that's equal to e to the negative 100 over 994.99. And you put that in your calculator, and that's equal to 0.904. Okay, so the final answer is that the probability it will not fail for at least 100 hours. The wait time probably the wait time is going to equal to 100 is 0.904. Okay, all right, and so that is the answer to example 5.13. It's an example where we use condition 2 to conclude we have an exponential random variable, and then we calculate. Actually, in this example, we're not given theta. We have to use a known probability and use a known probability to solve for theta, and then find another probability once we've found theta. Okay, because once we find theta, we now know the PDF for this exponential random variable, and then we can plug it into the integrand of this integral used to represent the probability we want. And then calculating the integral gives us the probability that we want. That the system probability the system will not fail for at least 100 hours. Okay? And that's example 5.13. Okay? So in fact, if the waiting time between events of a specific kind is an exponential random variable, with parameter theta, the number of events of this kind from time 0 to t is a Poisson random variable. With parameter lambda t is equal to 1 over theta times t. In fact, if the waiting time between events of a specific kind is an exponential random variable with parameter theta, the number of events of this kind from time 0 to t is a Poisson random variable with parameter lambda t, which equals to 1 over theta t. Okay? So if you have an exponential random variable, you can think of an equivalent Poisson random variable in that situation. Okay? So that's what this says. Okay, so let's keep going. I'd like to look more at the camera, though I find that as I'm focusing on the material, I can't quite look at you and write on the board at the same time. But, okay, so example 5.14 from example 5.11. What is the probability that more than 3 calls will arrive within a 5-minute period? Okay, so for example 5.14, from example 5.11, what is the probability that more than 3 calls will arrive within a 5-minute period? Good. Okay. Okay, so in example 5.11, the time interval minutes between calls arriving is an exponential random variable with parameter theta equals 0.5. Okay, so this was example 5.11. Time interval in minutes between calls arriving is an exponential random variable with parameter theta equals 0.5. Okay, so for that example, what's the probability of more than 3 calls will arrive within a 5-minute period? Okay, so we have an exponential. So write this. Okay, let's write the solution here. The time interval in minutes is an exponential random variable. With parameter theta equals 0.5. And so from the previous fact, we know we can think of a Poisson random variable. So so the number of calls from time 0 to t is a Poisson random variable with parameter lambda t, which is equal to 1 over 0.5 t. Okay, so from the fact before, we have an exponential random variable with a parameter theta equals 0.5. So we can think instead the number of calls from time 0 to t is a Poisson random variable with parameter lambda t, which is 1 over theta, 1 over 0.5 t. Okay, so let capital X equal the number of calls arriving within a 5-minute period. Then capital X is a Poisson random variable with parameter lambda equals 1 over 0.5, where t is 5. 1 over 0.5 times t, which is 5. And so that's equal to 10. So the probability of more than 3 calls in this 5-minute period is the probability that capital X, the number of calls, is greater than 3. And that's equal to 1 minus the probability that X is less than or equal to 3. And this is equal to 1 minus the value of the Poisson distribution at 0, 10, minus P of 1, 10, minus P of 2, 10, minus P of 3, 10. Okay? Because we want to know the probability of X less than or equal to 3. And so instead of thinking of the probability X less than or equal to 3, we can think it's the probability X is equal to 0 plus the probability X is equal to 1 plus the probability X is equal to 2 plus the probability X is equal to 3. And so we're subtracting that. Then we're subtracting the probability X is equal to 0, subtracting the probability X is equal to 1, subtracting the probability X equals 2, and subtracting the probability X equals 3. And those probabilities are for the Poisson distribution. So that's P of 0, 10, P of 1, 10, P of 2, 10, P of 3, 10. And so you calculate those probabilities using the Poisson distribution, and you get 1 minus 0.0104. which is equal to 0.9896. Okay, and so the probability of getting more than 3 calls within a given 5-minute period is 0.9896. Okay. Okay, so that's that example 5.14. So I'll give you a minute to look at it. Okay. So you probably need to watch these videos more than once. Okay, the material's getting harder than it was earlier in the semester. Notes. If there are on average lambda events of a specific type, within a unit time interval, then on the average the time between events will be theta equals 1 over lambda. Okay, so if there are an average lambda events of a specific type within a unit time interval, then on the average the time between events will be theta equals 1 over lambda. Okay, so for instance, if you had an interval, let's see, okay, so I've reused this a few times. Let's say you had an hour. Okay, so let's say you had 1 hour, and let's say you had the event happened 5 times, right? So your event happened 5 times during that 1 hour, right? And so lambda would be 5. Lambda's 5 because the event happened 5 times in that hour, in that unit time interval, right? So the unit of time is an hour. So let's say it happened 5 times in that hour. Then on average, the time between events is theta equals 1 over lambda. So if we're thinking of 5, if on average 5, if this event happens 5 times in an hour, then on average 1/5 of an hour is the length of time between when the events happen, right? And so if it happened 5 times in this hour, on average, you might think that they would be spread out. Right? And so the average would put them equally spaced in that hour. And so you would separate it into fifths. Oh, wait, I know what to do. Okay, so then you get so then you have 1/5 here, you have 1/5 there, 1/5 there, 1/5 there, 1/5 there. So there's 1/5 in between each. Okay, so let's say there's 1/5 of the hour between occurrences, right? So then we're just separating them into fifths there. And that's it. So you just wait 1/5 of an hour in order for the next event to happen on average, okay? So that's why theta is equal to 1/5, and theta is the average time between events. Okay. Because theta is you're thinking of wait time, and the time you're thinking of the number of occurrences. Okay, so the next section is 5.7.3, which is the normal distribution. Okay, so a continuous random variable capital X has a normal distribution. And is a normal random variable if its probability density function is defined as follows. Okay, so a continuous random variable x has a normal distribution and is a normal random variable if its probability density function is defined as follows. Definition 5.5. Let mu and sigma be constants with negative infinity less than mu less than infinity and sigma positive. The function f of x, which is equal to 1 over the square root of 2 pi sigma times sigma times e to negative x minus mu squared divided by 2 sigma squared for negative infinity less than x less than infinity is called the normal PDF. With parameter mu and sigma. Okay, so a continuous random variable x has a normal distribution and is a normal random variable if its probability density function is defined as follows. Definition 5.5. Let mu and sigma be constants with mu being a real number and sigma being positive. The function f of x equals 1 over the square root of 2 pi times sigma times e to the negative x minus mu squared over 2 sigma squared for any real x is called the normal PDF with parameter mu and sigma. Okay, so that's the equation. Mu is a real, sigma is positive, and so it's a formula. That's the PDF. Okay, so if you have a continuous random variable x with that PDF, then you can say it's a normal random variable. Okay, again, continuous random variable with this PDF is a normal random variable. you add the word normal with that PDF. Okay, and it's a normal PDF with parameter mu and sigma. Okay, so mu and sigma determine the exact PDF. Okay, so I'm going to erase this top part here. I'm going to put a picture here. Okay, so that's x, and that's f of x. So figure 5.7, a normal PDF. Okay, so that is the normal PDF. That's what the probability density function looks like when it's a normal PDF. Mu is right in the middle there, and it's symmetric about that axis. Okay, and so this is the most important PDF in probability because there are so many situations that it models in the real world. Okay, so this is extremely important. Okay, so what we'll do next is we'll compute probabilities using this PDF. And so we'll find probabilities by, okay, so 5.7.3.1, finding probabilities for normal random variables. Okay, so the first important thing to point out is that the normal PDF does not have an antiderivative. Okay, so the normal PDF does not have an antiderivative. Okay, so we rely on tables for its values. Okay, so normal PDF does not have an antiderivative, so we rely on tables for its values. So normally we would integrate and we would find probabilities calculating a definite integral. But when there's no antiderivative for this PDF, for this function, there's no antiderivative for f of x, we can't use the fundamental theorem of calculus to say that the value of an integral is an antiderivative evaluated from the lower limit of the integral to the upper limit of the integral. We can't do that. And so there are tables which will tell you the values for certain probabilities. And so you're going to rely on the tables in order to answer questions here. Okay, so table 3 in appendix table 3 in appendix C has values of the probability that 0 is less than x less than z for a normal random variable. So for a normal random variable capital X with parameter mu is equal to 0 and sigma is equal to 1. Called a standard normal random variable. Okay, so table 3 in appendix C has values of the probability from 0 less than x less than t for normal random variable x with parameter mu is 0 and sigma is 1, called a standard normal random variable. Okay, so you just use table 3 to calculate the values of these probabilities. Okay, because you can't integrate it because it doesn't have an antiderivative. Okay. Also, what's important to note is that the probability that negative z is less than x less than 0 is equal to the probability that 0 is less than x less than c. It's symmetric. You can switch. You could switch these two, and the probability is the same. And so that is true because the standard normal random variable is symmetric about the vertical axis at x is equal to 0. Okay, so but we should point out this is for a normal random variable x. This is for a normal random variable x with parameter mu is 0 and sigma is 1. I'm going to circle that also. Okay, and when we add those specific values to mu and sigma, mu is 0, sigma is 1, we add the word standard there. Then it's called a standard normal random variable. Okay, so it's a standard normal random variable when you choose those specific values, right? And so a normal random variable can have different mu and sigma, but when you choose those values, you get a standard normal random variable, and the table tells you the probabilities when it's a standard normal random variable. Okay, but we'll see how you can take any normal random variable and find the relationship between that probability and the probability of a standard normal random variable. So there'll be a way to translate the probabilities of a normal random variable to a standard normal random variable. And then you can use the table and this relationship to find the probabilities for your standard normal random variable. Okay, so you'll see what I mean hopefully later. Okay, so let's continue. So example 5.15, let capital X be a standard normal random variable. Use table 3 to find. So let capital X be a standard normal random variable. Use table 3 to find. So part A is the probability that 0 is less than x less than 2. Okay, so let's find that probability. Let's do it. Okay, so you use the table, and the table tells you it's 0.4772. Okay, so you go to table 3 in appendix C. So this is table 3 in Appendix C. Okay. And it'll tell you the probability that 0 is less than x less than 2 is 0.4772. And let x be a standard normal random variable. Okay, part B is find the probability that -2 is less than x less than 0. Well, by symmetry, that's the probability that 0 is less than x less than 2, right? Because it's symmetric about the axis, vertical axis, x equals 0. And so this probability, we already found, is 0.4772. And so that's the same probability as an A. C, the probability that 1.5 is less than x less than 2 is equal to the probability is equal to the there's a negative here. So it's probably -1.5 is less than x less than 2. Okay. And so then that's equal to the probability that -1.5 is less than x less than 0, plus the probability that 0 is less than x less than 2. This is equal to the probability that 0 is less than x less than 1.5, plus the probability that 0 is less than x less than 2, right? Because this is the same as this due to symmetry, just like in B. And so now you just use the table to find those two probabilities. The table says this probability is 0.4332 plus this probability, this one is this one, plus this probability, which is 0.4772. That's the other probability. So you add those two up and you get 0.9104. Okay, and so that probability is 0.9104. Okay, so that's C. Okay, D. Probably x is greater than 1.14. That's equal to the this is equal to 1 minus the probability that x is less or equal to 1.14. And so this is 1 minus the probability that x is less or equal to 0 plus the probability that 0 is less than x less than or equal to 1.14. And so this is equal to 1 minus the probability x is less or equal to 0, since it's symmetric about the line x equals 0. Half is to the left of that vertical line and half is to the right. Half is when x, the probability that x is less or equal to 0 is 1/2, and the probability x is greater than 0 is 1/2. This probability is 1/2, which is 0.5, plus this thing. You look in the table, so I'll put a squiggly line under it. You look in the table and you get that's 0.3729. Okay? And so that's equal to 1 minus that plus that, which is 0.8729. So 1 minus 0.8729, which is 0.1271. Okay, and so that's the end of that example. Thanks for watching this video. See you next time.